A very good morning. My name is Sri Ganesh. This is Levin. This is Kevin. This is Ali. First and foremost, I would like to thank you for watching this video, and special thanks to our supervisor, Dr. Aksha. Okay. Today, we will be presenting on sulfur dioxide emission reduction of flue gas thermal oxidizer, which covers problem statement, product market study, plant location evaluation, process cleaning, process flow diagram, icon simulation, heat integration, instrumentation and control strategy, HAZOP studies, plant layout, waste treatment, process economics and cost estimation, and finally conclusion. In 2014, the Clean Air Regulation, known as CAR 2014, is mainly enforced to replace the previous 1978 regulation. Given the flue gas condition from the existing thermal oxidizer, sulfur dioxide is need to be reduced in order to comply with CAR 2014 limits. Based on our client's request, our team is requested to propose a solution to reduce the SOx emission from flue gas in order to comply with CAR 2014 limit. Moving on to the product market study of sulfuric acid and methanol. Sulfuric acid is chosen out of the other products such as gypsum and sodium sulfate because it has a higher economical potential, which can be seen from figure on the left. As for the methanol is chosen out of the other products such as methane and syngas due to its higher economical potential, which is shown in figure on the right. Based on our market analysis, the price of sulfuric acid is 275 USD per ton and methanol is 450 USD per ton. Moving on to the plant location evaluation, there is 3 locations that is being evaluated, which are Malaysia Refinery Company, Penguin Refinery Company, and Petron Refinery. By using the ranking method, weightage of marks is given from 0, which is the lowest, to 5, which is the highest for each of the selection criteria. Based on our ranking method, Malaysia Refinery Company has the highest value because it has due to the factor of marketability and existing thermal oxidizer factor.
Thanks, Ganesh. So based on the client request to produce 2 value-added products, the product screening can be divided into 4: CO2 separation, SO2 separation, CO2 conversion to methanol, and SO2 conversion to sulfuric acid. Firstly, the SO2 separation. In this design, the Wellman lot process is selected due to its regenerable process and high SO2 removal efficiency. In terms of CO2 separation, the chemical emulsion is more preferable in which the true ammonia CO2 capture is selected due to the high CO2 removal efficiency and resistant to oxidative degradation. For the SO2 conversion, the wet gas sulfuric acid WSA is selected as it gives higher SO2 conversion of 99.7% by direct production of sulfuric acid without the formation of oleum. Meanwhile, for the production of methanol, there are generally 2 pathways, which are either through the direct methanol synthesis or the methane synthesis via the dry methane reforming DMR. For direct methanol synthesis, the CO2 is directly converted into methanol by supplying at least 3 times of hydrogen supply. For the second alternative, the CO2 is firstly converted into syngas with methane through the DMR process. From there, the syngas is then further converted into methanol with a lower hydrogen makeup requirement. Therefore, we have come up with 2 design alternatives. The difference between the 2 alternatives is the first design alternative produces methanol from carbon dioxide through the direct methanol synthesis. For the second design alternative, produces methanol via the DMR process in which the CO2 is firstly converted into syngas with methane as an intermediate product to produce methanol. Hence, by comparing these 2 alternatives, the second design alternative is selected as the desired process route and it shows great economic potential of generating $174 million per year. So based on the second design alternative, here it shows a process flow diagram before heat integration. In this design, the fuel gas is first fed into the SO2 absorber from the bottom with sodium sulfide as a solvent in order to recover the SO2 gas component. Sodium bisulfite is then formed and then sent to the evaporator to recover the SO2 gas through solvent regeneration. After the Wellman process, the dissolved gas are then sent to the chill ammonia CO2 process to recover CO2 gas through chemical absorption. Meanwhile, the rich ammonia contains high amount of CO2 is then sent to the CO2 stripper column for solvent regeneration. The CO2 gases are then regenerated and sent to the methanol synthesis unit. From there, the CO2 gases are then used as a feedstock to produce syngas with methane in a DMR. In order to maximize the methanol production, a hydrogen makeup stream is applied to the methanol synthesis reactor, and lastly, the distillation column is used to purify the methanol products in order to meet the sales validation of 99%. Meanwhile, the recovered CO2 gas are then sent to the WSA unit where the SO2 catalytic reactor is used to oxidize SO2 to SO3. From there, the SO3 gases are then condensed in water vapor to produce 98% purity of sulfuric acid in the WSA condenser. Therefore, with this design, the SO2 emission can be significantly reduced by 99.82% while comparing to the CAR 2014.
From there, based on our PFD, we are using the NRTL property package as it is suitable for a process with polar components and electrolytic mixture composed of ions obtained from salts such as sodium sulfide and sodium bisulfide. There are less than 5% deviation found when comparing the manual balance and simulation values. This proves the simulation accuracy and reliability. Heat integration is needed to reduce the cost by maximizing the energy recovered. After heat integration, 7% and 44% of heating and cooling requirements are removed, which gives us a total of 12% the total energy required. The PFD shows the addition of 3 heat exchangers made after the heat integration process. There are 7 main equipments in instrument and control strategy. In terms of reactor, such as DMR, SO2 catalytic converter, methanol synthesis reactor, height selector cascade control is used to maintain the reactor temperature and differential pressure by manipulating the feed flow rate. Next, heat exchanger maintains the outlet temperature of critical process stream by manipulating the outlet flow rate of stream. The same strategy is applied to cooler, which using cooling water as the medium. Last but not least, bypass steam flow rate is manipulated in the compressor using anti-surge integrated control to prevent any backflow into the compressor. This is the P&ID with all control strategies. Next, I'll pass the floor to Kevin.
Thank you, Hani. Next, for the HAZOP study. HAZOP study is a review of an operation to determine whether a deviation of intended operation can lead to undesirable consequences. HAZOP uses deviations such as flow, temperature, pressure, and guide words such as no, more, or less, with 3 nodes being studied, which includes methanol distillation column, the wet sulfuric acid condenser, and dry methane reformer. For today's presentation, the dry methane reformer is used as an example with the deviation, flow, and guide word no, with possible causes such as high blockage or leakage at inlet and inlet control valve malfunction, leading to consequences such as no reaction occurred, loss in production and economic, with recommended actions such as regular maintenance and inspection. Next, for the plant layout, this diagram will be proposed as our plant layout. The orange boxes in the middle are our process area, the yellow boxes are our product and raw material storage area, and the blue boxes will be the utilities, and the red boxes will be our emergency response. For the next section, I'm going to talk about the waste treatment part. The major waste in the plant is identified in 3 main phases, which are solid, liquid, and gas. The solid stream consists of sodium sulfate as the solid waste. Next, the liquid stream contains methanol as the liquid waste. Lastly, the gaseous waste contains carbon dioxide, carbon monoxide, methane, hydrogen, and methanol as the gaseous waste. The regulation followed for this project includes CAR 2014, which is the Clean Air Regulation 2014, and the Industrial Effluent Regulation in 2014. So firstly, I'm going to talk about the solid waste management strategy. The solid waste is generated as the purged product from Wellman Lot Process Unit from stream 49. Only 14.7% of the stream is needed to be removed as it contains sodium sulfate, whereas the remaining 85.3% of the liquid can be recycled back to the system. The sodium sulfate phosphate solid are removed through the sedimentation process, the sodium sulfate will then go through a dryer where any moisture content will be removed and stored before transporting it to the treatment company. The estimated solid waste disposal costs around 15 million ringgit, while the cost of removal for the solid waste per ton is 108 US dollar. For the liquid waste treatment strategy, the liquid waste only consists of 2.6% of methanol and the rest are water in stream 47. The biological treatment process of activated sludge system is selected because it is effective in consuming methanol even at the low concentration. Stream 47 will be mixed with activated sludge and air in the aeration tank before moving to the clarifier settler where the clean water will be removed and discharged into the drainage system. Some of the sludge removed from the clarifier will be recycled back to the aeration tank, while the rest will be sent back to the sludge treatment unit before sending it to a treatment company for disposal. Lastly, for the gas waste treatment strategy, Stream 74, which is the combination of Stream 12, Stream 41, and Stream 46A, contains carbon monoxide, methane, hydrogen, and methanol as the gaseous waste. The gaseous waste stream is sent to a closed thermal oxidizer for complete combustion of carbon monoxide, methane, and methanol before sending it through a filter and stacking it to the atmosphere. Currently, there is no regulation limit for carbon dioxide in Malaysia, but we estimated that the price of emitting carbon dioxide will be roughly 850,000 ringgit per year, with the estimation of carbon tax set to be 10 US dollar per ton of carbon dioxide emitted.
Thanks, Kevin. As known that the primary objective of a process plant is to make profit, here it shows the cost estimation in terms of capital expenditure CAPEX and operating expenses OPEX. For the CAPEX, the purchase equipment cost is estimated using the factorial method based on the equipment capacity, operating conditions, and the construction material. So by considering working capital and installation costs, the total capital investment is found to be around 105 million US dollar. Meanwhile, for OPEX, involve both direct and indirect operating costs, which include raw material, labor force, research and development, and etc. Therefore, by summing out all these, the OPEX of the plant is estimated to be around 208 million US dollar per year. On the other hand, the cash inflow for the plant operations is based on the sales of sulfuric acid and methanol. Therefore, based on the market price, it is estimated to generate an annual revenue of 289 million US dollar. To perform the economic analysis, several assumptions have been made as a basis for the study, which include the total project life is 18 years, in which the first 3 years of the project are allocated for the commissioning of the plant, with 15 years of plant lifetime. The plant operates at 8,150 hours per year, with an annual corporate income tax of 25% and minimum attractive rate of return of 20%. As shown in the slides here, it shows a discounted cash flow diagram for the project at MAR of 20%. From that, it observed that the payback period for the project is estimated to be 6 years before tax and 7 years after tax. Since the discounted cash flow rate of return is 44.25%, which is much higher than the 20% MRR, therefore, this shows that the project is economically feasible. Also, by analyzing the capital cost, the economic potential at level 3 is determined to be 92 million US dollar per year, which again proving the economic feasibility of the project. In conclusion, it is believed that all the client's requests are successfully met, in which a process plant is designed to treat the fuel gas by recovering and converting the SO2 and CO2 into sulfuric acid and methanol. Therefore, we will here end our presentation here. Thank you.